one, so let's start. Sasha is here again to give us a talk on chain algebras of finite distributive lattices and their properties.
Yeah.
Take it away.
Yeah, once again, thanks for letting me talk about my research. So yeah, this time is going to be about my research, unlike the previous talk. So this is the outline of today's talk. I'm going to define, well, you see it all yourself. I'm not going to, but so the first section is chain algebras of finite. So FDL means finite distributive lattices. Those are the only kinds of lattices that are going to appear. So, oops. Yeah, so we have L is a finite distributive lattice. We recall in my previous talk, I said that every finite distributive lattice comes from J of P, where P is some poset. And okay, so J of P is the lattice of ideals of a poset P. And an ideal is a downward closed set, subset of P. It's an if and only if. So, you know, it's a very convenient definition of a distributive lattice. An alternative definition. Let's label the elements of this lattice by variables t0 up until t whatever. And you will see why I'm starting from 0. I insist that the 0 goes to the, okay, so a finite distributive lattice has a minimal element, a unique minimal element, a unique maximal element, right? Because if you have two minimal elements, they're not comparable, and you can take their meat and you have something smaller than both. So that's why a finite distributive lattice always has, any lattice actually, any finite lattice has a unique minimum and unique maximum. So I insist that when we label our vertices, we give the smallest label to the min and the biggest label to the max. And I'm going to start at 0. You will see why. And to each maximal chain C in this lattice, they're all of the same length, by the way. So to each maximal chain, we're going to associate a monomial, which is going to be the product of the corresponding labels. So yeah, so if your chain goes between, I don't know, T0, T1, T2, and then finally T max, then you just multiply those T's, and that's going to be your monomial. We'll see an example on the next slide. And then the chain algebra of this lattice is just, you know, the toric ring generated by these monomials. So it's K adjoint all of these monomials. Yeah. Again, we will see an example on the next slide. And of course, the goal is to study how, you know, to study the algebraic properties of this algebra and the defining ideal, of course, and to connect them, to link those properties to the combinatorial properties of the lattice or the poset we started with. And let me show you an example. Of course, the example is going to be this. Those are going to be our two examples, right? And I'm going to erase those labels, maybe. Yeah, let me erase the labels. I'm just going to give it some other labels. So it's going to be the same lattice, but I'm going to call our vertices T0, T1, T2, T3, T4, T5, T6, and T7. I think that's the same as in that picture. Yes. Okay, so what are the maximal chains here? Well, 0, 1, 3, 5, 7 is a chain, or 0, 2, 3, 6, 7 is a chain, right? And I'm going to take all of these monomials and generate an algebra, and give me 1 second. It's the lattice we have seen in the previous talk. And yeah, so I'm writing here 1, 3, 5. I'm not writing a 0 and the 7 because every chain passes by 0 and 7 anyway. So all the monomials will be divisible by T0 and by this T max, right? And it doesn't hurt to just cancel out. It only hurts when your lattice is very, very small, right? When your lattice is like this or like this, then it's problematic when you just cancel out the min and the max. But otherwise, it doesn't really hurt. So the algebra generated by those truncated monomials is going to be isomorphic to the algebra generated by those full monomials. But so I'm going to truncate them, just, you know, because it takes less space on the slide. Like they don't fit if I write them fully. So the chains here are, the maximal chains here are, what are the maximal chains here? I'm going to write monomials. So M1 is, well, 0 is there always. So 1, 3, 5. So T1, T3, T5. That's the first chain. The second chain is 1, 3, 6, 1, 3, 6, and 7. T1, T3, T6. Then the third chain is 2, 3, 5, I suppose. Yeah, 2, 3, 5. M4 is going to be 2, 3, 6, I think. Yes. T2, T3, T6. And finally, M5 is going to be 2, 4, 6. So these are all the maximal chains. I canceled the T0 and T7, and now you might understand why I started at 0, because now I'm going to cancel it, and the variables go between 1 and 6. So this is my chain algebra. This is the chain algebra of this lattice by our definition. Oh yeah, I forgot to say it's a joint project with Lisa Niklasson, who is now in Västerås, I think. Yeah, in Västerås, in Mälardalen in Sweden. So yeah, so this is our chain algebra. And by the way, you can check this algebra is isomorphic to, so K of all of these monomials is isomorphic to, well, so what are relations? Well, you can see that the second monomial times the third monomial, I keep the ordering as it's written there. So the second monomial and the third monomial, they give me the same as those two monomials. And you can trust me, there are no other relations. So it's K of, there are 5 chains. So I'm going to write capital T1 up to capital T5. And I'm going to mod out by, what was that? 2, 3 minus 1, 4, right? And there are no other relations. So, or rather, that's really the generating set of this ideal. So we're interested in general, what does this algebra look like? What does the defining ideal look like? What are the properties and so on? Now I'm gonna talk about sortable sets of monomials and sortable lattices. It's a little bit different topic, but it's all gonna connect at the end. So consider the following set of monomials. Again, like it's one of those examples where you show one example and it's much more clear than an abstract definition. So I prefer to go by examples than by definitions, especially in this talk where the goal is to convince you, not to, be precise. So I'm gonna look at the 5 monomials from before, and actually they're written down here and there as well. I'm gonna show you how the sorting operator works. What does it mean to sort monomials? So I'm gonna write monomials M2 and M3. Where am I gonna write them? So M2 is this and M3 is this. I'm gonna write them as T1 times T2 times T3 times T3 times T5 times T6. That's my M2 times M3, right? I'm just going to write all the variables that are there. If needed, they're repeated, and in the non-decreasing order, right? So I write them down, 1, 2, 3, 3, 5, 6. Yeah. And now I'm going to underline the the odd positions, right? And I'm going to make a monomial of this. So that's T1, T3, T5. And the remaining, the even positions are T2, T3, T6, right? Did I do this right? Yes. T2, T3, T6. Now note that 1, 3, 5 is monomial 1. Yes, yeah, this is M1. And this was, I think, M4. Yes, this is M4. Right? So this pair, I call it unsorted because you input the pair, you get the output, and it's a different pair. So I call this pair unsorted. If I instead try M2 and M1, if you do the same thing with M2 and M1, you perform, I mean, I can do it here. So M2 times M1, what is it? 1, 1, 3, 3, 5, 6. Yes, that's correct. 1, 1, sorry, was it? Yeah, no, 1, 2, 3, 3. Yeah, 1, 2, 3, 3. Well, it was 1, 1. Oh, yes, yes, okay, yeah. It was 1, 1, yes. Yes, 1, 1, 3, 3, 5, 6. Then I'm going to underline the odd positions, and I'm going to underline the even positions. And this gives me, I think it gives me 1, 3, 5, which is M1, and M2. The other one is M2, right? So this is a quote unquote sorted pair. I call it a sorted pair in quotation marks just because, I mean, the only reason why it's not technically a sorted pair is just because I put it in the wrong order somehow, right? But it's morally a sorted pair, kind of. And clearly, if I now put them in the correct order, if I do the sorting algorithm on the pair, these are ordered pairs, right? If I do it on the pair M1, M2, I'm going to have M1, M2. So that's a genuinely sorted pair. So yeah, so a pair is called sorted if the sorting process gives you the same pair. It's a quote unquote sorted pair if it's sorted up to a permutation, and then otherwise it's unsorted. But note that so note that here, did you have a question? Yeah.
What if, like, this underlining procedure does not produce a monomial in your set?
Yes, exactly. Yeah. So yes. So the next definition exactly addresses this question. So a set of monomials is called sortable if this set is closed under the sorting operation. So you're right. It can happen that a set is not sortable, right? Like, for example, if you have, yeah, like x1 squared, and if you have x2 squared, and if this is your set, then clearly you're like, or t, I don't know, whatever, x1, x1, x2, x2, and clearly you have, this produces x1, x2, x1, x2. So you're right, this set is not closed under the sorting operation, but the one above, it was closed. You can trust me on this. You can.
Produces unsorted pairs. That still means it's sortable.
Sorry, once again.
So it's producing these unsorted.
Yeah,
pairs.
but the set is sortable. The set is sortable because it stays within the set. Whatever output of your sorting operator stays within the set. So yeah, so this set, for example, is not a sortable set at all. Now the set above is sortable, but you know, some of the sorting operators, some of the outputs of the sorting operators are, you know, not the same as inputs. This can happen. This should be already sorted.
But don't I get T1, T5, T4?
Wait, and what?
Which is not.
Let's see, M1 and M5, right? It's 1, 2, 3. It's 1, 2, 3, 4, 5, 6, right?
Oh, you have this sort. Okay, I know that's right.
Yeah, is it just 1, 2, 3, 4, 5, 6, right?
Yeah.
This is 1, 3, 5. That's in our set, and I think 2, 4, 6 as well. Yeah. Yeah, so it's again, yeah. It's actually a sorted pair even, yeah. Yeah. So yeah, so sets can be not sortable, like as you said, and then everything is bad. But even inside sortable sets, you can have unsorted pairs. Okay. Now, why am I interested in sortable sets? It's a theorem by Sturmfeld that says if you have a sortable set of monomials, then you take, so K of S denotes the toric ideal, the subalgebra generated by those monomials. So the defining ideal of that is going to be generated by sorting relations. And moreover, these relations form a Grobner basis for this ideal. So what does it mean? It means, what are sorting relations? So for example, if you look at the unsorted pair, clearly M2 times M3 is the same as M1 and M4, right? Like when we do the sorting procedure, the product of the monomials in the input is clearly equal to the product of the monomials in the output, right? Because we're just rearranging those variables, right? So this is a sorting relation. So if you take a toric ring generated by your monomials, these are relations among, right, among your monomials. So that's going to be inside, those relations are going to be inside your ideal, the presentation ideal, or whatever it's called, defining ideal. And the converse is also true. So for example, I don't know, if you consider this set, for example, this element, this 3-element set, right? This set is a sortable set, because if I sort those two, I get x1, x2, and x1, x2. So, but if you think of k of x1 squared, x1, x2, x2 squared, it's isomorphic to k of t1, t2, t3. And I mod out by the sorting relations. And the only sorting relations are, well, I took those two as an input, and I got this and this and as an output. So maybe I should have written x1 squared times x2 squared. So as an input, I put those two. As an output, I get this and this. And that gives me a sorting relation, meaning this times this equals this square. So I write it in the same order. So t1, t3 minus t2 squared. So and then Sturfes tells us that if your set is sortable, then you take all the sorting relations which come from sorting of these pairs, and those generate you the ideal, the toric ideal, which is a defining ideal of this toric algebra, which is quite cool. So in our case, in the case with those monomials, right? We have 5 monomials, right? So k of these 5 monomials is isomorphic to k of t1, t5. Now, the only sorting relation here is, you can trust me on this, is this unsorted pair. You remember the unsorted pair, right? 2, 3 equals 1, 4. So I'm going to mod out by t2, t3 minus t1, t4. Of course, you can mod out by t1, t2 minus t1, t2, or t2, t1 minus t1, t2, but that's just, so sorted pairs and sorted pairs in quotation marks, they don't really produce, they produce zero relations, right? But the proper sorting produces your proper relation, which you write down here, and that's the generating set, that's a generating set of your ideal. So in our case, the only real sorting is 2, 3 becomes 1, 4. And so the only really generator here is this. And remember, that's exactly, I mean, that's exactly all the generators that you need.
Do you need for the Grosvenor base?
Yes. So it's a Grosvenor basis with respect to any order, such that it has the following property. It fixes unsorted pairs as the leading terms. Yeah. So as long as this guy is the leading term and not this, and for all monomials or for all binomials, yeah, it's called a sorting order. So as long as your unsorted pairs are the leading terms, then it's a Grosvenor basis. So now I want to talk about, now I want to talk about sortable lattices. Clearly, because if your monomials in that might make a chain algebra, if they're sortable, then you know something about the presentation ideal, the defining ideal, right, of the toric ring. So okay, so I'm saying a lattice, it's always a finite distributive lattice. It's sortable if there exists a labeling on the vertices such that the chain monomials make a sortable set. And this really, you should find a labeling, because here the labeling was kind of good, right? But I can totally I can come up with a labeling on those elements such that the monomials are not sortable. The set of monomials is not sortable. So, But the definition says as soon as you have one labeling, then your lattice is sortable. Okay, so if there exists a labeling. So then clearly this example I showed you before was sortable, right? Because we found the labeling explicitly, we checked all the pairs, the output of the sorting algorithm, it produced monomials inside the set, so it was all good, right? And then I want to show you a non-example, and you might ask, oh, how do you even prove that, do you check all the labelings? It seems difficult to prove that something is a non-example, but let me show you something, and maybe you'll be convinced that it's a non-example, and that's this guy here. I'll show you why it's not why one labeling is bad. So this labeling is bad. Actually, every labeling is bad because I declared it's going to be a non-example. Let me show you why this labeling is bad, and let me show you why every labeling is going to be bad. So how is the labeling? Just row by row? Yes. So T1, T2, T3, T4. It's easier to just draw it from scratch. Yeah, so T1, T2, T3, T4, T5, T6, right? I mean, I can put T0 and T7, of course. Yeah. So what are the chains? What are the chains here? Well, let's see. So M1 is 1, 4, so it's 0, 1, 4, 7. It's one chain. T1, T4. M2 is going to be T1, T5. Right? It's this chain here. The next chain is 2, 4, well, 0, 2, 4, 6, right? I think it's, yes, M3 is, what is M1? M3 is, was it 2, 4? Yes, T2, T4. Then M4 is going to be 2, 6, I guess. Right? Is this the correct order? Yes. M5 is going to be 3, 5. Yes. And M6 is going to be 3, 6. So these are all the chains of this lattice. I'm going to cancel the 0 and 7 again. So why is this set not sortable with this labeling? Because let's sort M2, M3. M2 times M3 is 1, 2, 4, 5. 1, 2, 4, 5. I'm going to underline the odd position and the even positions, and I'm getting T1, T4, and T2, T5. Right? And T1, T4 is a chain, it's fine, but 2, 5 is not. So this set is not sortable with this labeling, right? In any case. But why is it not sortable under any labeling? And that's because you can check in this specific example, you can just plug it in Macaulay 2 and ask what's the defining ideal of the storic ring, of K of all of those monomials, right? What's the defining ideal? And turns out the defining ideal is just generated by this one guy, and it's a cubic guy. And well, if you had some kind of labeling, then your thing would be quadratic, right? Because if your set is sortable, then the defining ideal would be generated by sorting relations, and those would be quadratic. And here it's a cubic relation. So we don't need to check all the orderings. We just know it's not possible, right? Because, yeah, because we have a cubic relation. So this set is just not sortable, no matter what labeling you choose. Yeah, and that's what it says here. Yeah. So now we would like to classify all sortable finite distributive lattices because the defining ideals in that case is nice somehow. I mean, it's quadratic, I mean, the monomials are sortable and those quadratic monomials form a Grobner basis, so it's all super nice. And this is the highlight of our paper. This is, I would say, the main theorem. And the main theorem goes as follows. So we have a finite distributive lattice, and I think I'm going to write it down because I'll need them. I'll need the statements. Okay. So let L be J of P, or I can just say let L be some finite distributive lattice, whatever. Then the following are equivalent. One, L is planar. And well, if you yeah, if you were here for the previous talk, you know what planar is. I can repeat it later. L is sortable. The defining ideal of the chain algebra has a quadratic Grobner basis. No, okay, K of CL. That's the chain algebra. Has a quadratic Grobner basis for it's quadratically generated. Is quadratically generated. And 5, the last one. The chain algebra is a Hebbe ring. I'm not saying of what, not of the same lattice, but yeah, we will see this later. So these are the 5 equivalent statements. Between 3 and, I mean, you can also put Koszul, for example, because, you know, quadratic Grobner basis implies Koszul, Koszul implies quadratically generated, but I didn't put it here because, I don't know, I didn't have enough space. This is the strategy of the proof. We couldn't do it in a circle, so we did a circle between 1, 2, 3, and 4, and we connected 5. So if you look at all of these implications here, so 2 implies 3 is obvious because, well, I mean, it's not, oh, sorry, it's not obvious, it's just by Sturmfeld, right? Sturmfeld tells us if we have a, if we have a sortable set, then, you know, we have a quadratic Grobner basis. This is just by Sturmfeld, right? 3 implies 4 is obvious. 5 implies 4 is by definition because the Hebbe ring is quadratically generated, right? So really what we're left to prove is 1 implies 2, 4 implies 1, and 1 implies 5. 4 implies 1 is not really that inspiring. I can briefly tell you how 4 implies 1. So quadratically generated implies planar. So roughly speaking, I'm going to do the contrapositive, right? So if something is non-planar, a non-planar lattice means that in the poset where it comes from, there's an antichain of size at least 3, like here, right? Maybe higher, right? Because planar means dimension 2, means this width is at most 2. But if not, then this width is at least 3, so you can find an antichain of size 3, and that thing will produce you a cube inside your lattice. And this cube already gives you a cubic relation. We have seen it, right? Oh, it's not written here, but if you have a cube, you have a cubic relation, and it cannot be killed. Sure, you have a lot of more stuff in your lattice because you have more stuff in your poset, like maybe somehow there's stuff going on, but that cubic relation is going to survive. So yeah, even a tiny cube inside your big lattice already produces a problem. So it produces a cubic relation. So that's why it cannot be quadratically generated. So 4 implies 1 is, I explained you the philosophy of it. It's not the most exciting proof, but so what I'm most interested to present here is 1 implies 2 and 1 implies 5. Those are the goals that I want to explain. Those are the proofs that I want to explain the ideas of, right? Okay. So this is 1 implies 2. So 1 is, yeah, I wrote it down so that you don't forget what is 1 and what is 2, right? So 1 is L is planar and 2 is L is sortable. So I'm saying consider the bottom to top, left to right labeling. And when I say this, it sounds extremely vague. It sounds like it's hand waving, but remember that if your thing is planar, that it's embeddable on the grid, right? On the rectangular, on the square grid in R2, right? In Z2, right? So when I say bottom to top, left to right, I can make it precise. In fact, I can even, like, remember what I said, right? So like, since it embeds on the grid, I can attach monomials here. I can say, this is going to be X direction. This is going to be Y direction. I can say this is 1. This is X. This is X squared. This is Y. This is XY. This is X squared Y. This is XY squared or something, right? And this is probably X squared Y squared. So when I say bottom to top, left to right, I just go, you know, degree by degree. So look, here's just degree 1 monomials, here's degree 2 monomials, here's degree 3 monomials. So bottom to top means degree by degree, and left to right means I take them lexicographically. So clearly 1 is less than Y less than X, less than XY less than X squared, less than X, I mean, so bottom to top, left to right is well defined. That's what I'm trying to say. No? Sorry, yes, degree lex. Yes, you're right. Yeah. Within each degree, it's lex. Yes, exactly. So yeah, I just wrote it like this because, you know, it's clear what it means. But if you want more precision, you can say you attach monomials in this way and you take degree lex on those monomials. Okay. So we give such a and if you remember, that's exactly how the labeling was before, right? There was T0, 1, 2, 3, 4, 5, 6, 7, right? So we give it such a labeling, we just agree. And we're going to prove that this labeling is a good one. So the idea is we can show that a pair of monomials, so by monomials, I mean chain monomials, right? A pair of chain monomials is unsorted if and only if the corresponding maximal chains cross, and I'm going to explain what it means. So what does it mean that 2 chains cross? So here everything is happening on the square grid, right? I say that 2 chains cross if they go somehow like this, right? Again, this can be well defined. This is actual hand waving because I'm waving my hands like quite literally, but this can be defined properly. So 2 chains are non-crossing if one of them stays weakly to the left of the other. So for example, this chain and this chain are not crossing because they have the common beginning, then they go away from each other. They are allowed to touch, they're allowed to have common intervals, but they're not allowed to go like inside each other like this, right? So that's what it, so that's what it means that the chains are crossing, and we can prove that the monomials are unsorted if and only if the chains are crossing. And when you sort your monomials, this corresponds to resolution of the crossings. And let me show you what I mean. So those are 2 chains, right? So the red monomial corresponds to 1, 3, 6. I wrote it somewhere, 1, 3, 6. That's M2. The green one corresponds to 2, 3, 5. And you remember, those were exactly the guys that were not sorted. Remember, we inputted 2, 3, and we outputted 1, 4, right? Like the sorting procedure was, I can write it again, right? So like the sorting procedure was inputting M2 and M3. We're going to write it 1, 2, 3, 3, 1, 2, 3, 3, 5, 6. The sorting procedure, if you remember, produced a 1, 3, 5. And 1, 3, 5 is M1. And the second one was 2, 3, 6, which is M4. Right? So we can show that monomials are kind of not sorted, like here, if and only if the corresponding chains go one inside the other. And when you do this procedure, you resolve the crossings. So you see, like, I obtained M1 and M4, and M1 is exactly the orange chain, right? 1, 3, 5. And 1 corresponds to 1, 3, 5, which is this orange chain. I hope you all can see colors, right? And the other one is 2, 3, 6, which is exactly M4 here. Right? So this is something we can prove. And then clearly the set is sortable, because you can take two chains and you can always resolve them, and they produce other chains again, right? So this procedure, it takes in two chains, and whatever it is producing is again two chains. So your set is indeed sortable. By the way, this does not work in the non-planar case. Like, look what happens here, for example. Remember how we were trying to sort M2 and M3 here? Here, M2 was 1, 5, right? And M3 was 2, 4, right? The procedure is like the sorting produces 1, 4 and 2, 5. So it kind of tries to, like, if there was a vertex here, like imagine if there was an extra vertex here, right? Then the chains would be 1 blob 5 and 2 blob 4. And the sorting procedure would have created this and this, and would have been fine. But there is no vertex. So the sorting procedure creates an approximation of this. The best approximation is this and this, but this is not a chain, right? But if this vertex was here, everything would be fine, right? And it's exactly because there are crossings without vertices. So that's an intuition why it doesn't work in the non-planar case. I already explained why it doesn't work in the non-planar case, because you have a cubic relation, but that's like an intuition, right? Like you cannot play the same game in the non-planar case. Like your resolution doesn't produce chains.
Are you really thinking that about three-dimensional? Because you're kind of going over and under, and like they don't actually.
Yeah, but yeah, exactly. So it's not a cross, you're right. But then I can't say, right, that non-sorted pairs correspond to crossing chains, right? Because this pair is still not sorted. Like this M2 and M3, you need to sort them, right? And yeah, they're on top of each other, right? So, and that's kind of why it doesn't work, because what does it even mean to sort? Yeah. But in that case, you can always sort them. Yeah, so you can see this as non-crossing because they go one on top of the other, or you can see it as crossing, but then there is no vertex here, so the resolution of crossing is not really, doesn't work the way you want. So yeah, you can see them as just, yeah. But in 2 dimensions, everything works exactly as you want, right? Like chains, like if 2 chains go like this, then, the resolution produces this chain and it produces this chain, and it's all nice and great. So, and you can see that, we sort the red and the green monomials. We already did the sorting, and it produced the yellow and the blue monomials. So that the 2 and the 3, they were sorted into, 1 and 4. And we're going to say that this chain C1 is going to be the minimum of the 2, and C4 is going to be the maximum. So I'm going to say the one to the left is going to be the smaller one, and the one to the right is going to be the bigger one. So this sorting kind of produces 2 chains. One is which is like to the left of both. So the sorting of those 2 produces 1 chain which is to the left of both, one that is to the right of both, kind of. And we call it the min and the max. Now, yeah, so now we proved 1 implies 2, right? Planar implies sortable, because, in the planar setup, unsorted pairs correspond to crossing chains. And when you try to sort them, the procedure produces, the resolution of crossings. So that part is done. Well, kind of. I mean, I didn't explain the proof, but so now I want to talk about chain algebras of planar distributive lattices as Hebbe rings. Now I want to prove this. I want to say if L is planar, then the chain algebra is actually a Hebbe ring of something. And that's maybe the most exciting part of the talk, I would say. Okay, we already did all of this morning. I decided to keep it for 1 minute. I don't know. So yeah, we have, let me remind you that a Hebrew ring is just, you know, you have a lattice, not necessarily distributive, and you have these Hebrew relations here. You take two elements and you take their meet and join, and you make the corresponding binomial like this, and you collect all of these, and that's your generating set. The definition makes sense for also for non-distributive lattices, but then the ring is not toric, so we're not interested. And a lot of algebraic invariants of Hebrew rings can be computed in terms of combinatorics of the poset and lattice you started with. So yeah, so that we already had this morning. So now I want to realize my chain algebra as a Hebrew ring. So now I want to prove this implication. So again, I have a planar distributive lattice, which intuition-wise, it means it fits on the square grid in R2. It fits on Z2. So I'm going to introduce partial order on maximal chains of our lattice, right? I'm going to say that one chain is bigger than the other if it's more to the right. Again, this is a bit hand wavy, but this can be well defined. So if your chains are not crossing, right, then one of them is to the left and one is to the right, kind of weakly to the left and weakly to the right, and the one that is to the left, we're going to declare it as smaller. And if your chains are crossing like this, then you say they're not comparable. It's just a poset on chains, right? So in this here, this is the smallest chain, this is the biggest chain, and this red and green from the slide before, they're not comparable, and you know, so you can make a poset like this. It's a different poset. And one of the key propositions is that with the partial order that I just defined, it's not just a poset, it's actually a lattice. So the chains themselves form a lattice, and it's actually a distributive lattice. And it's, moreover, I'm going to show you an example and you will see immediately how this works. But this is a distributive lattice. So for example, here, I have this orange chain. This was orange, right? This is like the smallest chain. Now there were red and green that are, you know, they're both bigger than this orange, but they're not comparable. So like this, we have 5 chains in total. It's going to be fast. Now there is this chain that was bigger than both red and green. That was blue, right? And there is this chain that just doesn't really do anything. So this is the lattice of chains, the way I defined it, right? So, and the theorem says that it's always going to be a lattice. Moreover, it's a distributive lattice with the meet and the join being, you know, being exactly this min and max that I defined. So if you have a situation like this, if you have like 2 chains going like this, then the meet is going to be this left thing, and the join is going to be this right chain. And this is a distributive lattice, and I'll show you an example. So now we have a planar finite distributive lattice. We know that what is the chain algebra once again, right? So we have K of variables indexing chains of L, right? That's how did we define it, right? We have we know that it's sortable, right? So we can write it this way. We can write K of variables indexing, when I say chains, I mean maximal chains, modulo sorting relations, right? And I proved before, right, that sorting corresponds to this you know, resolution of crossings. So I can write my sorting relations this way, right? So I input 2, and then like this were the red and green, and this were the orange and the blue, right? This we already proved. Now we also know that the Hebrew ring of this other lattice, now it's a lattice of chains, right? It's a different lattice. This is not L prime. Like now we remember how we define Hebrew rings. It's again K of variables indexing the vertices of your new lattice, right? And the vertices of your new lattice are exactly the chains of the old lattice, right? Because that's how I defined it. I defined this new lattice L prime as consisting of chains of the old lattice. So the variables here are the same. They're indexed by the same things. And modulo the Hebbe relations. I already proved that the Hebbe relations are exactly the same as those sorting relations. So they're not just isomorphic, they're literally the same, actually. So we have realized the chain algebra of L as the Hebbe ring of this L prime. If you look at this L prime, there is like, so remember, so this is the orange one, this is the first chain, this is the second chain, this is the third chain, this is the fourth chain, this is the fifth chain. And if you look at this L prime, well, you remember how the Hebbe rings are, how the defining ideal are, like the product of this minus the product of this. That's exactly the relation we have, right? 2, 3 minus 1, 4. That's exactly the relation on the chains we have, the only relation. Let me show you a picture, because you can understand this much better in a picture. This is our lattice, our L, and you have to tilt your head a bit. It's just the same lattice as here, but you tilt your head a little bit. And yeah, so it's embedded on the grid, right? So I am going to embed it on a grid. It's embedded on a square, actually, on a rectangle. So I'm going to draw, this is the leftmost chain, right? This is the smallest chain in this lattice of chains, in this other bigger lattice. I'm going to draw the other lattice. Well, not bigger, in this case, it's actually smaller, but now I'm going to draw the lattice of chains. So the orange chain is the leftmost. So it's the one here. That was orange in this slide where we were sorting chains, right? So this is T1, I'm going to call it T1, and I'm going to identify it with the corner that it cuts from the top. So I'm going to identify it with this dashed corner. Now, this was the red chain, one of those two chains that we were sorting, right? Like there were two crossing chains, right? The red and the green. And I'm going to identify this T2 with this bit that it cuts. Now there was a green one. So you see the red and the green, they're crossing. Like if you look at like if I'm just going to do this, if you look here, they're crossing chains. So I'm going to draw T2 there and T3 there, and I'm going to identify them with Young diagrams they're cutting. Now there is T4, which was the max of both, and there is T5. So now you see how it's actually a interval of Young's lattice, because you can identify those chains with the bits they cut from the corner, from the, I mean, top right or bottom left, it doesn't matter. It's a matter of convention. So, and now look, you compute the Hebbe ring of this, and it's again the same 2, 3 minus 1, 4 all over again. So, and it's again, I mean, it's isomorphic to the chain algebra. So you can see it as the Hebbe ring of this lattice now. And I think this picture kind of explains how you do it. So now, of course, if there is a distributive lattice, you might be asking, what's the poset where it comes from? So we have this L prime here. What is P prime? Where does it come from? It turns out that you can put vertices inside the boxes here and connect them. And how do I connect them? Well, like remember how I said the orange one that was top left, kinda, that was the smallest one. So the logic is right and bottom is big, top and left is small. So, you know, if this 5 is going to be bigger than this 3 and this 2, actually, remember how to go from I told you, right, how to go from lattice to the poset, right? You just, so our lattice is like this, right? How do you go to P? Well, you take the joint irreducible elements, right? You take guys that have one lower neighbor, which is this, this, and this, right? This 2, this 3, and this 5. And you take a poset on those. The 2, the 3, and they're both smaller than 5. So that's your poset from which this lattice comes, right? And that can be recovered by placing dots into your boxes. That we also proved. Yeah. So yeah, this could have been a little bit difficult, all of this, but yeah, but the point is that a planar, if you have a planar distributive lattice, then the chain algebra of this lattice can be identified with the Hebbe ring of another lattice. And that other lattice is made of chains of this lattice. So I'll briefly say something about the non-planar case, because we know a lot about the planar case, all of these equivalent statements. We don't know much about the non-planar case, almost nothing. We know the dimension of this ring. And by the way, in the planar case, this formula specializes to the number of boxes increased by 1. So for example, if you look here, there were 5 chains, 1 relation between them. So this was dimension 4. And the poset that we ended up with was this P prime. Well, I mean, there was this thing, right? So the number of boxes here is 3, and you increase it by 1, and it's 4, and it's exactly the dimension of this ring, K of 5 variables modulo 1 equation. The dimension is 4, and you can see it by counting the boxes and increasing by 1, because this formula specializes. And this formula agrees with Hebbe's formula, because remember, as I said, right, during my last talk, we know the dimension of a Hebbe ring. It's exactly, you know, it's exactly the number of elements of the poset P prime increased by 1, and the elements of poset P prime, they're indexed by the boxes here. So it makes perfect sense. So as it should, right? So it agrees with Hebbe's formula of the dimension of a Hebbe ring, and it would be really bad if it didn't, right? So the initial ideal of the defining ideal is square free, and therefore the algebra is normal in Cohen-Macaulay domain. This we know even in the non-planar case. But otherwise, computations in Macaulay too, they get very heavy, very fast, like computing a smaller, like even a smallest example, for example, in dimension 4 is already very difficult. So we know nothing about, about the non-planar case, unfortunately. But the planar case we understand pretty well. So these are the references, and thank you.
Are there any questions for Sasha?
Yeah.
I had one when you were making your set of boxes and you come back a couple slides.
Yeah.
I wasn't clear, but yeah, right here. What is the labeling A2, A3, and A5? What is that referring to?
It's relating to, so the join, so this was the first chain, this was the second chain, the third, the fourth, and the fifth, right? The join irreducible elements that make the poset correspond to 2, 3, and 5.
I also have a question. So the non-planar case, well, I guess this is a general thing about finite distributive lattices. Like, can you predict anything about what the width of the chain poset that you're describing is? So like, you went from the 3 squares and you got this smaller one, which was also 2-dimensional.
Oh, in general, it explodes. I mean, in this case, it becomes even smaller, but think about it, the number of chains is very big in a bigger lattice. So, like, the number of chains is big. So it seems like this L prime is going to be much bigger.
So if that's the case, though, like I guess in the learning seminar talk, you said that if it was dimension 3 or higher, then the Hebbe ring was not a domain.
No, a Hebbe ring is always a domain if your lattice is distributive. A Hebbe ring is not a domain when your lattice is not distributive.
Sorry, it's conflating it. Okay. Okay. Are there other questions?
So, correct me if I'm wrong, but you only define these chain algebras from a distributive lattice?
Yeah.
But you could define them for any lattice, right?
Yeah, someone has done this. Someone has done pure posets. So pure means every chain, every maximal chain is the same length. And they were like, yeah, why not just define it more generally?
You don't have to get
Huh. No, we don't know. We haven't looked at it. Yeah, that's the problem. Like all the proofs, they rely on this lattice being distributive. So we all often in our proofs relate to this, or we refer to this poset where the lattice comes from. So I don't have any intuition. It was just a nice thing to start with, but someone has done it. I don't know if it's ever going to be a Hebrew ring. In non-distributive, for non-planar lattices, we get cubic relations. So no. Otherwise, I don't know. But yeah, but you can generalize it to a lot of posets, right? I suppose.
Other questions? If not, then let's thank Sasha again.